A really important thing to not do is to do the inductive step backwards. And I know this might sound a little bit funny to say, but it's a really easy mistake to make, and it's something that I see all the time. The inductive step never goes backwards. And what do I mean by the inductive step going backwards? Um, it's tempting sometimes to try to write a proof by induction by maybe you do the base case okay, and then what you do is you assume that p of k plus 1 is true, and then simplify it down to something that you might know to be true, or simplify it down to p of k or something like that. So you assume p of k plus 1, and then you show that that implies p of k. Don't ever do this. Don't do this. Don't do this. Don't do this. And the reason why I say don't do this is that this is an invalid technique. Sometimes it might seem like it's working, and sometimes you might be able to do something that feels like a proof of a correct statement that way. But this is an invalid technique, and what I mean by invalid is that you can use this technique to quote unquote prove theorems, quote unquote, that are not correct. So you can be deceived by this. You can ultimately find yourself believing things to be mathematically true that are not. So here's an example of the dangers that can happen when you do this. So here's a theorem. I'm going to put it in quotation marks because to emphasize it is not true. So here's the theorem. For all n greater than 0, it's the case that 2 to the power of n is greater than or equal to 5 to the power n. Okay, obviously this is not true. So if you want to verify that, you can try plugging in, let's say, n equals 2 and seeing what happens. So this alleged theorem is not true, but if we allowed ourselves to do induction backwards, we might think that it was true. So here's our alleged proof. So for our base case, we'll choose n equals 0, because our theorem was supposed to apply for all n greater than or equal to 0. So if we check this, we have 2 to the power of 0 equals 1, which is also equal to 5 to the power of 0. Our inequality that we're trying to prove is not strict here. It says greater than or equal to. So actually, the base case is fine. Nothing wrong with the base case. N equals 0 is not a problem. But now, if we go to the inductive step, we're going to do induction backwards. So we're going to assume that 2 to the power of k plus 1 is greater than or equal to 5 to the power of k plus 1. This is our assumption. Then, what do? We're going to simplify. So if we say, okay, 2 to the power of k plus 1 is greater than or equal to 5 to the power of k plus 1. Okay, that's where we started. I'm just going to take out a 2 and a 5 from each one. So all of these steps are algebra. So 2 times 2 to the power k is greater than or equal to 5 times 5 raised to the power k. And then more algebra, I'm going to divide through by the 5. So I'm going to get 2 over 5 times 2 to the power k is greater than or equal to 5 to the power k. And guess what? If I just eliminate the 2/5, if I just forget the 2/5 existed, I would make this side of my inequality larger. And that's okay because my inequality points this way. So if 5 to the power k is less than this whole thing, it's definitely also less than whatever I would get if I dropped the 2/5. So that means that 2 to the power k is greater than or equal to 5 to the power k. So my inductive step that goes backwards, my backwards inductive step, so 2 to the power k is greater than or equal to 5 to the power k, as was to be shown. This backward step, where I started with p of k plus 1 and proved that that implied p of k, that all went okay in the sense that I did successfully show that p of k plus 1 implies p of k, but I proved an incorrect theorem. This is not true. I am not allowed to do this because if I do, I'm going to get myself in trouble. A little more specifically, what's going on here is that, in fact, this statement is false. P of k plus 1 is false. And if I have an implication where the antecedent is false, the implication is, in fact, always true. And that's what happened here. This was false. And so I was able to derive something, I was able to do a derivation, and the implication is true whenever the antecedent is false, but that doesn't make what comes next true. The implication is true, but that doesn't make the consequence true at all. So because I've made this logical violation where I've considered essentially a vacuous implication, by doing induction backwards, I've written what feels like a good proof, but is in fact an invalid proof of an incorrect theorem. So remember, when we are doing proofs by induction, you always, always, always have to start with p of k and then prove that p of k implies that p of k plus 1 is true as well. It has to be in that order. It cannot go in the other direction.